Hello, welcome back to Statistics and Mathematics YouTube channel. Today we are going to start our studies on t-test for the mean, right? So that's the hypothesis testing for the population mean when our population standard deviation is unknown. That's mainly what we are going to discuss today. So that's t-test for the mean. So what do we mean about t-test for a mean? The t-test can be used when our n is less than 30 or when the population is normally distributed and our population standard deviation is unknown. So in short, what we are trying to say here is that we use the t-test. In short, what we are saying is that we use the t-test when our population standard deviation, this one, is unknown, and whether our n is less than 30 or n is greater than 30. We use what? Our t-test to perform that analysis. So the main thing that you have to take note of is that when our population standard deviation is unknown and either our n is less than 30 or our n is greater than 30, we are going to use what? Our t-test. So how will we perform the analysis, right? So when we come here, we have what we call the t calculated, right? So the t calculated is equal to x bar minus mu divided by small x divided by square root of n. So you see that this is more or less similar to the test statistics for the z-test, right? It's more or less similar to the test statistics for the z-test. But what make it different is that for the test statistics for the z-test, we are having what? Our sigma, right? That's the population standard deviation. But when we come to the t-test, we have what we call our sample standard deviation. So this is called what? The t calculated, right? This is called what? The t calculated. So we compare this t calculated with our critical value from the t-test table, right? But I want to show you something here, right? So we are going to compare it with our degrees of freedom. So this is how you get our degrees of freedom from the t distribution table, right? We have t of alpha comma n minus 1, t of alpha divided by 2 comma n minus 1, right? So after calculating our t calculated, we compare it to what? Our critical values. We use t subscript alpha comma n minus 1 when we are dealing with what? One tail test, and we use t subscript alpha divided by 2 comma n minus 1 when we are dealing with what? Two tail test, right? So the n minus 1 that you can see here is called what? Degrees of freedom. So we are just going to subtract 1 from the observation that what we have. But before we jump into an example, two questions to solve, I would like us to learn how we can get our critical values from the t distribution table before we engage ourselves with some questions, right? So for question 1, we are just saying that So for question 1, we are saying that find the critical t value for alpha. Find the critical t value for alpha equals 0.05 with a degrees of freedom of 16 for a right tail test. So this is basically a one tail test that's still to the right, and our alpha is given to us as 0.05 and our degrees of freedom is given to us. So don't get yourself confused. Don't go and subtract 1 from this 16, because we were not given n, right? We were given the degrees of freedom straight away, so you are not going to subtract anything out of it, right? So here our alpha is equal to 0.05 and then our degrees of freedom is equal to 16, right? So this is how we are going to do. So here we are going to have t subscript 0.05 comma 16, right? So you are going straight to the t distribution table to get our critical value. So you are going to locate 0.05 at the column and 16 at the row side, and then where they meet will be our critical value. So just a minute. So this is the t distribution table of which we have used it before, right? When we were treating the confidence intervals, I did a video on that. I taught you how you can get your critical value from it, right? So if you haven't watched the videos on confidence interval, yes, for the population, you kindly go and watch so that you really understand the t-test. Yeah. So for here we have what we call the rows and what? The columns, as you can see here. So for the columns, we are having our alpha level is one tail test. So if our alpha level is one tail test, this is where basically you are going to base, because it was tail to the right, which is a one tail test, and our alpha was given to us 0.05. That's 0.05, and then we have our degrees of freedom to be 16. So we are just going to map this one to that where they meet, and you can see that they are meeting at what, 1.746. So 1.746, that will be our answer for the t-test, right? So it was still to the what, to the right. And let's move on to the next question. It said find the critical t value for alpha equals 0.01 with a degrees of freedom of 22 for a left tail test, right? With a degrees of freedom 22 with a left tail test, right? So this one is still to the left. So this two is what, one tail test, right? So we'll be having t subscript 0.01 comma 22, right? So let's go to the t table, just locate 22, and then it was 0.01, which is one tail test. So let's go and locate 0.01. So 0.01 is here. I'm just going to trace it down. Please, I'm coming, just a minute. We are just going to trace it down, right? And then when you trace it down, you can see that this is our critical value. But note, you see, this is our tail to the left. This is coming. So you can see that this is our tail to the left. So it will be negative, right? It is tail to the left, so it will be negative. So we are going to have negative t is equal to negative 2.508. For this one, it was still to the right. That's the reason why we leave it just like that. But if it's still to the left, you are going to negate it, negative 2.508, right? And then for the question 3, we are just saying find the critical values for alpha. For alpha is equal to 0.10 with a degrees of freedom of 18 for a two-tail test. So this is a two-tail test. So for this, we are going to have t subscript alpha divided by 2 comma n minus 1, right? So t subscript alpha was given as 0.10 divided by 2 comma n minus 1, and the n minus 1 is already calculated. We are having it to be what, 18. We are going to have t subscript 0.05 comma 18, and when you map it from the table, we are going to get t is equal to plus or minus 1.734, right? So this is what you are going to have for the for our answer, right? So let's jump to good examples, right? So that we will really appreciate whatever we have discussed so far. So for question 1, it says a medical investigation claims that this, I'm coming, just a minute. A medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigators' claim that our alpha is equal to 0.05? So this is very simple, right? So right now he said a medical investigator claimed that the average number of infection per week at a hospital in southwestern Pennsylvania is 16.3. So here our population standard deviation was given to us to be what, 16.3. And then a random sample of 10 weeks had a mean of 17.7. So a random sample. So the sample here, our n will be given to us as 10. Note, the n is not degrees of freedom, right? The n is the number of observation, right? So here our n is 10, and our sample mean is 17.7. Then he said the sample standard deviation, right? So here our sample standard deviation too is also given as 1.8. So this sample size, so here will be x. So with this criteria, and alpha is equal to 0.05. So with this criteria, we could see clearly that our sample standard deviation is given to us. So since our sample standard deviation is given to us, we are going to use what we call the one sample t-test for the population mean, right? And then we have to set our hypothesis. And you could see clearly here that this is what a two-tailed test, because we are having H here. It's a two-tailed test. So here we're going to have H naught is to mu is equal to 16.3. And then H1 will be mu is not equal to 16.3 at an alpha of what? 0.05. Right? An alpha of 0.05. So we just have our T here. Right? This is our T. So our T will be equal to x bar minus mu divided by x divided by square root of n, where we will just substitute. Our x bar was given as 17.7, our mu was given as 16.3, and our x was given as 1.8, and our n was given as 10. Just substitute them here. When you do your addition, when you do your subtraction, your division and square root, we are going to get 2.46. And then we have, it's a two-tailed test, and our alpha was given to us 0.05, right? Let me check well before. So our alpha was given to us as 0.05, and our n was given to us 10. So here, since it's a two-tailed test, we are going to have t subscript alpha divided by 2, comma n minus 1. So our alpha was given to us that, so it will be 0.05 divided by 2, comma 10 minus 1. We are having t subscript 0.025, comma 9. Note, here the degrees of freedom was not given to us. We were given only the n. That's the reason why we are subtracting 1 from it. So don't just get yourself confused, right? So you are going straight to the table and just locate this one to get our critical value. And when you go to the table, we are having two-tailed test. So we are having 0. So we are having 0.02, right? We can locate 0.02 here, right? We were given two-tailed test, which is 0.05. So when you divide it by 2, we are going to get this one, right? So 0.025, and trace it down and locate the degrees of freedom, right? Trace it down and locate. So 9 to this one, we are having 2.262, right? That is what we are having. So when you come here, you have 2.262. So I have to use the diagram to, explain a lot of stuff for you, right? So here, we are just going to locate. Since it's a two-tailed test, we are going to have positive 2.262 and then negative 2.262, right? So here, we are just going to locate the positive 2.262 here and the negative 2.262 here. Anything beyond this positive 2.262 will be at what? The rejection region. And we could see clearly that our critical value lies at the rejection region. So since our the T critical is less than Z calculated, we are going to reject our H naught, and hence conclude that there is an evidence to and hence conclude that the claim the claim is that the average number of infection is what? 16.3. Yes. So that is that for that question. Let's try our hands on these questions too, right? Let's try our hands on what? These questions too. Let's continue. So here we are having an educator claims that the average salary of a substitute teacher in a school district that is less than $60 per day. A random sample of a school district had a mean of 58.88 and a standard deviation of 5.08. Is there enough evidence to support the educator's claim at an alpha of 0.10? Hallelujah. So we are having this one here, and then let's jot our parameters down. So here we are having our population mean to be 660, and then our sample mean to be 58.8, and then our standard deviation to be 5.08. So it is a sample standard deviation, and our alpha to be equal to 0.10. Our n2 was given to as 8. And then you could see clearly that this is what a left tail test because of what the less than. So let's set our hypothesis. We are going to have h naught is to mu is equal to 60, mu is less than 60. So this is what a left tail test at an alpha of 0.10, right? So when you calculate for your critical value from the T table, right now you have done enough on how to get your critical value. So for this one, just get the T distribution table and calculate the critical values on yourself. So we are going to have our critical value to be negative 1.415. Right, that's our critical value. So the T will be x bar. The T will be what? X bar minus mu divided by small x square root of n. You are just going to substitute the parameters we wrote down here. You are going to get negative 0.624. Right. So this will be what our T calculated, and then this is what our Z critical. So you could see that our Z critical is greater than our Z calculated. It means that it will fall at what? They fail to reject what region. So there is no enough evidence to support what they claim, that we said that our mu, right, is equal to 58.8. So there is no enough claim to do that. So this is the end on hypothesis testing for the population mean when our standard deviation is unknown. So please, if you are new to this channel, kindly subscribe, like and share so that this video will get viral for your friends to also watch. Thank you. Bye bye. See you in our next video.